Another great thing of 802.11n, and you probably have heard about it, is MIMO, multiple in, multiple out. By the way, the official way of saying it is not MIMO, it's MIMO. Although it's multiple in and multiple out, it was voted as having to be said MIMO. So the idea is to be able to send more than one signal at any given time. So you remember multipath, where we have these echoes working against us and going back to the station at different points in time. Over time, while 802.11 was being worked on, vendors made fantastic progress in the ability of the receiving chipset to ignore those echoes and just distinguish the main signal from all these echoes and basically isolate itself from multipath issues. So multipath is not so much an issue anymore by the time 802.11 is being developed. So much though, so that they say, why don't we actually take advantage of these progresses we made in the technology and actually use this capability we have to isolate one signal from these echoes and actually send two signals at the same time. And on two receiving radios, we should be able to isolate one from the other and distinguish one from the other. Why not? And they decided to do it, and that's what MIMO is about. So be careful, you're sending on the same frequency, right? You're not using different frequency. This has nothing to do with the channel aggregation. You can use 20 or 40 megahertz channels, but in both cases, you send more than one signal on that given frequency. You send two or maybe more signals at any given time. So multiple inputs and multiple outputs is actually reversed in the logic. Input is actually what you send into the antenna. Output is what the antenna sends into your circuit. So multiple output is what you receive, and multiple input is what you're going to send out. That may be counterintuitive. So to contrast this MIMO technology with what we had before is called SISO, single input, single output. And in those days, they were thinking of maybe having some hybrid modes where you will have some old stations that may still have only one single radio, but may be compatible with 11n. So you may have some variations, some stations having two radios, so they would be able to send or receive two signals, some others having only one. So you would have all combinations between MIMO, SISO, and anything in between, SIMO, MISO. Because to be able to send two signals at the same time, you have to have two radios, right? Two radios and two antennas, one per signal you want to send. So this is called a radio chain, the combination of the circuit, the radio, and the antenna. So with 11n and MIMO, you can have more than one radio chain. And of course, to receive more than one signal, you also need more than one radio chain. Each of the radio chains being in charge of isolating one signal from the other, and each chain receiving one of the two signals you have been sending. The signal you send is called a special stream. That's the stream that you want to send to your client, and that is going to be received on any given receive chain. So all that is combined, right, on the same frequency, which means that there are multipath issue all over. But because we're so good in isolating ourselves from the multipath issue, we can do it for one signal and we can do it for two signals. And if you have more than one radio chain, there are a few things you can do. One of them is what we described, send more than one signal at a time. So you send one symbol from one antenna and you send another symbol at the same time from the other antenna. You see in my description I say A, C, E, B, D, F because you're not sending a frame from one antenna and another frame from the other antenna. Each frame is made of symbols, and what you're sending is one symbol from one symbol from the other, then one symbol from one, etc. So you have to recombine these two at the receiving end to be able to combine them and get the frame. So it's distribution of symbols, not two frames sent from each of the radios. That technology, when you send these symbols over two radios or more, is called spatial multiplexing. This spatial multiplexing supposes that the receiving end also has two radio chains, right, to receive these symbols on each side and then recombines them at the other end. But you can do something else. You can do what we call transmit beamforming, which is that you're going to actually send the same signal from both of your radio chains. But what you're going to try to do is to shoot those signals so that as they reflect with multipass, they hit the client exactly at the same point in time and the same point in space. So that client may have one radio chain or may have two radio chains, it doesn't matter. The result is that it's going to receive those two signals at the same time and in the same point in space, of course, which means that the resulting signal is going to be stronger. And if the signal is stronger, you can do two things. You can either move away and get a larger cell, because at a farther distance you will still be able to reach the client. Or you can get a better signal at any given point, which means that you don't move, but instead of getting a slow speed, you get a slightly higher speed because the signal you get is of better quality. In most cases, with the evolution of technology, we tend to have smaller cells. So in most of the times, what was done is to not increase the size of the cell so much, but increase the speed of your clients inside your existing cell size. All right, transmit beamforming relies in the protocol on the idea that the client is going to tell you if the two signals you received were synchronized well enough to be received exactly at the same time. So there is what we call the sounding mechanism, which is just a test mechanism, a text exchange of messages to verify the environment and make sure that we align this transmission properly. Thing is, the 802.11 amendment described many ways of doing this exchange, so many that nobody figured out what way would be common to every vendor, and no client vendor implemented any dynamic feedback mechanism. So you would think that transmit beamforming never happened, but in fact, in the Cisco network, they used the signal coming from the clients, even without any specific training or sounding frames, as we call them. We used just a normal signal from the client to understand the environment and use that understanding to send the frames in the right coordination on the way back, which means that even without any feedback from the client, Cisco access points can use that transmit beamforming to increase the signal power at the client level. That Cisco technique is called client link, and that's something you need to know for the CCNA exam. We'll spend a little bit more time on that feature in the upcoming lessons. So sending the same signal on one client that may have only one single receive chain is transmit beamforming. But if you look at the client side, and if you're receiving signal from two radio chains, because you do have two radio chains, then regardless of how many were sent, you can take one from one chain, take the same signal from the other chain, and combine them together. And that's called maximal ratio combining. That is pretty much transmit beamforming, but seen from the client side. If you have two radios, you take advantage of these two radios to take one signal, add it to the other one, which is the same, and the result is a stronger signal. So to do MRC, you do not need to have any specific sounding mechanism, right? You just need to be able on the client side to receive a signal, be able to identify where you are in your symbols, receive the same symbol on the other side, and just realign them together. Of course, you cannot do special multiplexing and MRC at the same time. MRC relies on the fact that you're going to take the same signal on both radios to combine them. So you have to choose. If you want to use two signals, then you have one signal on each radio. But if you send one single signal, then if you have two receivers, you can combine them together and get a stronger signal. And that's MRC. 802.11 allows you to use all the way up to 4 special streams. Most of the time, you will not find any device having 4. Why is that? Well, because when they started in 2009, many vendors said 2 streams, we see how that can be done. 3 streams, it's too complicated. How do we tell one from the other? It's too much computing. Then, as you know, today we do have 3-stream clients. And many vendors said just a few years back, yeah, 3 streams happen to be possible. 4 streams, no, it's too complicated. So today, 11N is kind of going away because we have 11AC coming out. But max we can see with 11N are 3 streams. And if you have devices that have a battery, those devices do not want to have 3 radios because that's going to consume so much power. So most handheld devices, phones, have 1 stream only because they want only 1 single radio to save on battery. If it's a larger device, like a tablet, they may have 2. But only laptops with a big battery have 3 today. This is going to be true if you continue with 802.11ac, where you can have more streams. We'll see that in a few minutes. But then the performance, of course, depends on what technology you use in 802.11n. 20 MHz, 40 MHz, short guard interval, or normal guard interval, long guard interval as you call them, 1 stream, 3 streams. You see, you can get all the way up to 600 megabits per second in theory in the protocol. Practically speaking, if you have 3 streams, you get all the way to 450. That's supposing that you use 40 MHz channels, 3 streams, and short guard interval. Then depending on what client you have in your hand, it may be getting max performance anywhere in this table, depending on its physical characteristics. So how does that translate into data rate, speed? Well, in fact, the name we had before, data rate, was a bit misleading. You remember when we were talking about protection with 11B, we said that 54 megabits per second is the data rate, the speed, but that's the speed at which you send your frame. Many people thought that 54 was actually the throughput. because we're saying speed or data rate. So they thought it was what you were getting when downloading things to your laptop. So to avoid that confusion in 11N and 11AC, they renamed that concept from data rate to modulation coding scheme, MCS, which is something technical enough and confusing enough that nobody would think that is actually a throughput. So it's basically the same concept, it's just renamed to avoid confusion. The data rate you would get, or the MCS you would get, depends of course pretty much on what type of modulation you use, how many streams you get, and of course how much channels you're going to use. But here again, as you see, we're using the same OFDM techniques, BPSK, QPSK, 16 and then 64 QAM. And the logic is, as you go up in one stream, you go from BPSK to QPSK, from QPSK to 16 QAM, from 16 QAM to 64 QAM. And then if you add a second stream, you continue numbering your MCSs down, and then you start MCS 8, and that's BPSK with 2 streams. And then you have MCS 9, which is BPSK with 3 streams, and then 10 would be QPSK, etc. You go all the way to 15, and then again you start 16, 3 stream, etc. And that's why the speeds you have are of this range of BPSK to 64 QAM, and then the number of streams determine what number in the MCS you're using. What about protection? Remember my BG protection? That was pretty inefficient. And you know, the 802.11 people didn't make it inefficient on purpose. It just happened to be inefficient because of this protection necessity. So for 11N, they thought, we're not going to make the same mistake again and not use that RTS-CTS mechanism. It is still allowed for backward compatibility, but as a matter of fact, only CTS to self is allowed. But they introduced another idea to say, what you want after all is to tell at slow speed, in our case G or A speed, that you are going to send something faster. You don't need an exchange to do that. What you're going to do is to send your frame, but at the beginning of your frame, you're going to have a chunk, a header bit of your frame that is going to be modulated at slow speed. And behind that, you have the rest of your frame that is modulated at higher speed. Because of that first chunk of your frame sent at G speed or A speed, the A and G stations are going to hear that and say, oh, there is a duration field in there that says you're going to speak for that duration. Okay, I stay quiet. And your nav is being reset to whatever value. And then the rest of the communication behind is sent fast and you don't understand it, but it doesn't matter. You're not listening, you're just waiting. So a common question you will get will be, wait, how do you send something slow at the beginning of the frame and then the rest is faster? It's going to go over the beginning of your frame. How does that work? Keep in mind that in Module 1 we saw that the wave is going at speed of light. There is no different speed in the wave itself. It's speed of light all the way. The only difference between those two sections of the frame is the density of zeros and ones that you modulate in each part of that wave. So in the first part, the density is not very high, which allows you to use the default OFDM with 16 QAM, 16 4 QAM, or BPSK, QPSK. And then in the later parts of your frame, you use a higher density of your wave, and maybe you have more than one signal in that modulation. And that's what makes it 11N. But the wave itself always travels at speed of light, so there is no collision of one part of the frame to the other. It's just a subsequent part of the wave. Does that work well? Yes, it does. However, with the idea of 20 and 40 megahertz channels, we have a new problem that we didn't have before. And the problem is the channel size. Imagine that you have this 802.11a access point on channel 40. And then, of course, you have a B client, which is 802.11n, so it's A or N, right? And then you have on the left side the 802.11n access point, which is on 36 and 40. So there is a problem on channel 40, as you can tell. Thing is, of course, the B client, sorry, I should say client number B because it's using 11N, it's not 802.11b. So client number B understands that channel 40 cannot be used because it hears access point on channel 40. But the 802.11n access point is too far away to hear the 802.11a access point on channel 40. So what happens? Well, what happens is that when B needs to send traffic to the access point on the left, it's going to understand that channel 40 cannot be used because of the access point on channel 40 on the right side. So it's going to use only channel 36, and communication is going to be successful. But now, when the access point wants to respond, it's going to listen to the air and say, well, 36 is free. 40 seems to be free as well, it doesn't hear the other access point. So it's going to send traffic, of course, on both channels, And of course, because of the access point on the right, that will create a collision on channel 40, which means that traffic will need to be resent. So you see, the 802.11n protection works well for BG/N protection or N/A protection, but they didn't think of channel size protection. So there are some cases where you have this kind of issue. In a Cisco network, though, there is this feature RRM, where the channel assignment is automatic, and there is a detection of channel being free or not, where this kind of issue does not happen. But if you define your channel statically, then you may have that type of issue, and a loss of traffic efficiency on channel 40 in that case.